under these circumstances, with a large portion of his legions left to garrison his main camp. He would not risk it, so he disengaged.
Okay. Howdy. I'm sorry for it. Right. Yeah, I'm alright. I just attended from CAC, so I didn't get any tickets, but still it delayed me a little bit. So, okay, give me a second. Okay. Okay, so people in the Zoom, can you hear me?
Yeah.
Great, yeah. Okay. Okay, first of all, I have some announcement that, yeah. First of all, quiz. We will have quiz today, but at this point, it will be from 4 p.m. to midnight. So, because, yeah, I actually uploaded it in the hour ago, but I just checked that this upload is paired. So I will re-upload it soon and let you know when you can take it. So as usual, it will be done in WebAssign. So I think that, yeah, at 4 p.m., you can see the quiz in the WebAssign. That's first announcement. And second one is that, yeah, I already said in the email that exam 3 was disclosed, so you can see the result of exam 3. And also I sent the grading scheme of the exam 3 from the emails, so please check your answers in the website. And if you have any question, then please let me know before the Friday night. Yeah. So, okay, Friday. So please check it. And the last, the homeworks, deadline of the homework will be extended. So chapter 13 deadline is in the Sunday, this coming Sunday, and chapter 14 deadline is this, next coming Sunday. And chapter 9 deadline will be the Sunday in the Thanksgiving. So please be aware of that. So yeah, so I think that there were lots of questions on chapter 13. So maybe if I have a time, then I'll review it with you in this course. So after finishing this chapter 14, then I will go back to chapter 13 and answer some questions with you, right? Okay. Do you have any question? Okay, great. Then let's deal with the number 5, hidden here and Huntington method in operation mode. So in the previous one, we uses we run the Jefferson method and Hamilton method and Webster method. And all these are the one apportionment method, but after 1941, the current House of, current Congress of United States used that Hill-Huntington method. So it is just keeping the relative differences. It is devised to keep the relative differences from instead of the absolute differences, because sometimes relative differences much more matters, especially for the smaller stage, right? So to do this, first of all, again, as usual, you need to compute the standard divisor first. And for the second one, you need to compute the quarter of the each state. So these two steps are just same as previous method. So they are just common. But in the third step, it just round each quarter according to the geometric mean of this the round down of Q and round of Q. So that Q star is geometric mean. So instead of using just round up or down for Gaussian function, we use the geometric mean of two numbers between the two integers between the exact number, right? And then the other two method is similar to the Webster method. So if we just do such a rounding, and if total number of seats is not correct, then call the crunch apportionment as n and find the divisors. So if number of seats needs to be increased, which means that our n is less than the house size of house, then use this di plus. But if n is greater than the size of house, then uses this di minus, where pi is just population of the each ice state. And ni is just current apportionment of ice state. And using this, you can adjust this using according to this. So if the number of seats needs to be increased, which means that the apportionment n is less than the house size, then assign a seat to the state with the largest di plus. But if the number of seats needs to be decreased, which means that the current apportionment is greater than the size of house, then remove the seat from the state with smallest di minus, right? So it is, so this part is the same as the Webster's method, right? So the difference is it uses geometric mean, whereas Webster's method uses just the Gaussian integer of the number, so which means just the integer which is closest to the exact number. And also this uses +1. Instead, Webster's method uses plus 0.5 or minus 0.5, right? So that's the main difference. So yeah, do not try to remember everything, but just be familiar with your hands by calculating some examples. So let's deal with example 5.2. And I will just want to open the prescribed route to avoid my mistake. So let's deal with this example. Okay, so let's return to the school district that received 46 computers to distribute to 5 high schools. And I muted. So yeah, 5 high schools based on the number. So here, it is just exactly the same example we did in the last time. But here we need to use this Hill-Huntington method. So instead of calculating in case of Webster's method, we calculated this number. But in here, we need to calculate this Q star. So for Q star of this 3.2036 is just square root of 3 times 4, because 3 and 4 is just the nearest number to the Q in the left side or right side, right? And this number is almost the same as 3.4641. And the next one is the geometric mean of 5.8321 is just square root of 5 times 6, which is square root of 30. And it is almost the same as 5.4772. And geometric mean of square root 1 times 2 is just square root of 2, which is 1.414 something. And geometric of mean of 18 point something is square root of 18 times 19. And if you calculate it using calculator, it is almost 18.4932 something. And geometric mean of 17 point something is 17 times 18. And it is almost same as 17.4929, something like that. So then you can just round it quarter according to the Q star. Oh, sorry. So here is rounded according to Q star, right? Instead of this one, so this one is used for Webster's method, right? But in the Hill-Huntington method, we use the rounded of the geometric mean instead of the actual Q, right? So in that case, the North High School has quarter 3 because 3.4 something is less than 3.5. And so, and the South one has, oh, give me a second. So, yeah, in the South, in the case of South, it is 5.4 something. So it should be rounded to 5. And in the East case, it should be rounded to 1 because 1.414 is less than 1.5. And in case of the West case, it is just rounded to 18. And in case of Central case, it is rounded to 17. So if you add all the numbers, then 26 plus 18 is, you can get 44, right? So here, we have 2 more computers left, right? 2 more computers are remaining. So we need to adjust this quarter using this method. So here the number, the current apportionment is 46 in our case. So here n is 46. And so the number of seats, in this case, number of computer, should be increased. So we need to use DI plus in here. So first of all, we need to calculate DI plus in here. And in this case, so this is our new N1, N2, N3, N4, N5. If we just labeling north, south, east, west as 1, 2, 3, 4, 4, 5. So here, first equation should be the population 39 over Ni, which is 3, a square root of 3 times 4. And if you calculate this number, then give me a second. I will just use my calculator. Yeah. So I don't know why today is a little bit miserable for me because my prescribed calculation is wrong. So that's why I need to put this again in my calculator. So yeah, so this number should be 11.2583 something. And for the next case, it is 71 over square root of 5 times 6 and 71 over square root of 5 times 6 is almost 12.9627 something. And in case of East, it is 18, which is population over square root of 1 times 2. So here, 18 over square root of 1 times 2 is just 18 over square root of 2, which is almost the same as 9 square root 2, or 12.7279, 79 something. And in the case of West, 2 to 3 over square root of 18 times 18, 19. Then 2 to 3 over square root of 18 times 19, which is almost the same as 12.0584. So, okay, I just use it in another one. And in the last one, 209 over square root of 17 times 18. 209 over square root of 17 times 18. It is almost the same as 11.9477 something. So this is the case when we need to increase. So we need to choose the stage with the largest DI plus. And here, the largest one is came to the south. So adjusted apportionment is here. The other stage should be the same, but in case of the south, it increases one more case. So it should be 6. And the other ones are same. And then again, we need to increase one more computer. So you need to calculate the I plus 1 again. Then all other values are same. And except this, the second one, because second one apportionment should be changed. So and in case of second one, it is 71 over square root of 6 times 7. And 71 over square root of 6 times 7 is 10.955 something. But again, yeah, here the greatest one is this east, right? So here the final apportionment should be 3 and 2 and 6 and 18, 17. And we are done, right? Okay, do you have any question on this process? Okay, sure. Yes, so in the first adjustment, I just add one computer to the second line, right? That's because the DI of the second line is the greatest one number. Yeah, one to the greatest number and calculate DI plus again, and also give one to the other greatest number and calculate DI plus again, and so on. Yeah, I did twice because there are 2 computers remaining. If there are 3 computers remaining, then we did it just 3 times, right? But in this case, only 2 computers are remaining, so that's why I did it twice. So what Abby's question is that, yeah, so I just added the computer to the south because if we just do rounding the quarters on according to geometric mean, then we already just give the 44 computers. So therefore, there are 2 computers remaining, so we need to distribute it for other states, right? And to decide which one will get this remaining computer, I just calculate DI plus. Then the south has the greatest DI plus, so I will just give 1 computer to the south. And next, I just recalculate this DI plus again, and then you can see that east is the greatest one among all, east has the greatest DI plus among all others. So I will give the last computer to the east, then we are done, right? So that's the process of Hill-Huntington method. Okay. Do you have any question? Great. So here the adjusted divisor is this 12.7279, which is just this number, right? So the final one is called adjusted divisor. Okay. Then if you don't have any other question, then let's deal with the other cases when what we need to do use the DI minus. So let's return to the small town example. So who are working together to reorganize their country presentation. So there are 8 council seats and use the Hill-Huntington method to distribute those seats. So this is also the same example in the previous lecture, but we will use just different numbers here. So here, again, we have the population and pre-calculated Q here. So Q star is, for the first one is 3 times 4 with square root, which is 3.4641. And in the second example, it is square root of 2 times 3. So it is the same as 2.44949. And in number C, it is square root of 1.1 times 2, which is square root of 2. So it is almost same as 1.4149, 1.42. And in the last 2 cases, it is 0 times 1, which is just 0 for both cases, right? So again, if you just got rounded quarter using the geometric mean, then what you can get is 3, 2, 1, 0, 0, right? Yeah. I don't know why. Okay, yeah, 3, 2, 1, 0, 0. So again, we have 6 seats in here. So in this case, we need to calculate the DI plus. But when you just calculate this DI plus, then first number should be 862 over square root of 3 times 4. And this should be, okay, CI62 square root of 3 times 4. And it should be, okay, I also did it here. CA62 over square root 3 times 4, which is the same as 1114.8633 something. And in the next case, the I should be 2818 over square root of 2 times 3. And in this case, again, what we have is 2818 over square root of 6, which is 50.4436 something. And the next one is 181 over square root of 1, 2. Then in this case, it square root of 1 times 2 is the same as 1330.0678 something, right? But in the next case, what we need to do is 500 over square root of 0 times 1. But you know, dividers cannot be 0, right? So it is actually goes to positive infinite. So I know that you didn't learn about the infinite concept or infinite, but actually, so when your number in the divider goes 0 very closely, then your whole number should goes to higher, right? So for example, if your numerator is just 1, but your divisor is from 0.5 to 0.01 and 0.0001 and so close to 0, then your whole number should be goes high, right? So in this case, we just write down it plus positive infinity and write down it as positive infinity. And that's the same case hold for both cases. Then definitely positive infinity is the most greatest one among all others. So in this case, first adjusted seed goes to one of them. So here, but there are no way, but here, yeah. If you see about both two numbers, then still this 500 is greater than 21. So we will just give this one seed for here first. Yeah, I know it's a little bit difficult concept for you because yeah, even if they are the same infinity, but we can kind of give some order between those states and infinity. But in this case, we have the same divisors, but numerator of the this first line is greater than numerator of the fifth line. So that's why we just give one seed first to the first line first, and or other one just same. And if you just calculate the next one, then the next divisor, oh sorry. Then again, or others are same. Is 633. And all those numbers for others are same, except this new number on the first line. So here, our new number should be 500 divided by square root of 1 times 2. And this is almost the same as 500 divided by square root of 2, which is 353 point something. And still this one is positive infinite. So here, this one is the greatest one. So we need to give the seed for the smallest this number. So okay. Then we can just, you know, apportionment of, we can just give all seed distributed. And there are questions from June that I thought for, Dawson says that I thought for geometric mean rounding, if Q is greater than Q star, then we round up. So for C, shouldn't it round up to 2? So here, geometric mean is 2.44949, right? And this is less than 2.4, 2.5. So that's why I rounded it to the 2, right? So even if we use this one or this one, both are less than 2.5. So that's why I rounded it to 2. Okay, do you have a question? D. We are looking for the Q. The question from Dawson is that we are looking for the second Q of the second line. Mhm. So we have 2 zeros in the rounded quarter, right? But using that one, we can calculate DI plus, right? But in case of that DI plus goes to positive infinity, right? Because there is nothing divide this number by 0, right? So that's why we choose the first line, because the number divided by 0 is called infinity, especially positive infinity, and positive infinity is just created for or among all others, right? Just because we just choose the one, we just choose the greatest number of DI, right? We just choose the first line. Then we will give one seed. Then we can just do the same procedure again. So does it make sense? Or great. Yeah. Mm-hmm. Mm-hmm. Yeah.
Gets me.
That's good question. So what our question is that when we just calculate the DI first, then we will use the divisor as 0. But in the next time, I will use the divisor as square root of 2, right? This is because by the adjusting, this change it from 0 to 1, right? So that's why I use square root of 1 times 2 instead of 0 times 1. Does it make sense? Okay, great. And there are some questions in the Zoom. 1.6. You mean C. So what Dawson's question is that the geometric mean rounding, it means that in the third line, this 1.657 is greater than 1.5, so it should be 2. But when I said about rounded quarter in Hill-Huntington method, we use Q star instead of the Q, right? So we use Q star, and if you just calculate this Q star on C, it is 1.4142, which is less than 1.5. So that's why we have the 1 instead of 2. Does it make sense, Dawson? Great, yes. Okay, do you have any other question? Okay, so when you calculate this DI plus, then please use the round adjusted seed. So at the first time, you need to use this rounded quarter, but after doing this procedure, you need to use adjusted seed to calculate your divisor because apportionment changes, right? And Harry says that is the quiz tonight going to be over chapter 13 or 14 or both? The quiz will be about the chapter 13. Yeah. Okay. Okay. Do you have any other question? Good. Okay, great. So let's do one more example. So here, let's return to the university's 100 student worker position. So use the Hill-Huntington method. Before going out, you can see that in the result, result, right? And see that if you have very small portion, then in the Hill-Huntington method, you can get a seed, right? But in the Webster's method, they didn't get a seed, right? So that's why, it is in my opinion, but that's why smaller states we love this Hill-Huntington method because even if their state is smaller, but you can have at least one seat in the Congress, right? So that's why the United States Congress, Congress of United States takes this method. So let's deal with example 5.4. So let's return to the University 100 student worker position. So here again, we have some Q's in here. So first of all, you can calculate the Q star first, and this should be square root of 42 times 43, which is almost same as 42.497. And square root of 26.27 is almost same as 26.4952, and square root of 29 times 30 is 29.49576, and square root of 1.1 times 2 is equal to 1.4142. So here, this Q star is determined by the integer part times integer part plus 1 with square root, right? Then from this, you can just calculate this rounded quota Q star, or rounded according to Q star. Then first one should be 42, and second one should be 26, because 26.952 is less than 26.5. And third one should be 29, because 29.495676 is less than 29.5. And this 1.4 goes to 1. So if you add all the numbers, then what you can get is 98. So still we have 2 seats remaining. So if you calculate this DI plus, then first one should be 5565. Okay, divided by square root 42 times 43. Oh, sorry. And this number should be so it is almost the same as 130.95023. And in the next example, 3471 divided by square root of 26 times 27 is 3471 divided by 26 times 27 is almost same as 131.00445. And in the next example, 3A64 divided by square root of 29 times 30 is equal to the 131.00186 something. And the last one, 197 divided by square root of 2 is 139.300 something. So here the greatest one is 139. So the adjusted seat should be the all other ones are same except the last one, right? 42, 26, 29, but the last one should be 2. So we add 1 seat for the last one, but still we remain 1 seat. So we need to calculate this DI plus again. Then when you can get is that the all other ones are just same because their seats do not change it. But in case of 2, we need to calculate again. In case of last one, we need to calculate again using the different changed seat. So here it is 197 divided by 2 times 3 with square root. And if you calculate this number, then it should be 18.4249 something. So here the greatest one should be the second line because yeah, that's the greatest one. So we need to add 1 seat for the second line. So here the last adjusted seat is 42 with 27 and 29 and 2 is still 2. And if you add all the number, you get 100, right? Okay, question? 20, oh yeah, so what I did is just choose the greatest divisor from among all, then add 1 to that seat. So in the step 1, in the when you have just distributed using the rounded quarter, then I will use calculate DI plus and pick the greatest one. In that case, it's the first row, right? So I will just give 1 seat to them. Then I will just calculate again about divisors because seats are changed, right? The number of seats are changed. But in the first 3 lines, their number of seats are not changed, so their divisor should be the same, right? But the last line, their number of seats changed, so I just recalculate the divisor again. Then I will choose the greatest one among all other divisors, right? That's the second line. So that's why I add 1 seat to the second line. Yeah, add it by 1 and calculate divisor again, add it by 1 and calculate divisor again. You can just do the same procedure until you have to distribute all the seats, right? If there is 2 seats, then still you need to add it by 1 and 1. Yeah, see, just 1 and calculate again, 1 and calculate again. Yeah, so that's good point. And okay, sure. Mm-hmm. 26.527 in the rounded quarter. So in the rounded quarter, this square root of 26 times 27 is 26.49 something, right? Yes, not the cube first. Yeah. So in that case, we need to round down because it is less than 26.5. So when you do it the rounded quarter in the Hill-Huntington method, use Q star for your rounding down or up instead of Q, right? Great. Okay, so the question from classroom is one is that, yeah, if we have some 2 or 3 more remaining seats, then how do we distribute it to the parties? And the answer is that just do it by 1 by calculating your DI plus or DI minus, and give this seat to the give 1 seat to the other and calculate divisor again and give it 1 seat to the other and so on. So just do the same procedure. And in case of Hill-Huntington method, rounded quarter is used to Q star instead of Q. So this one is for Webster's method. but this one is for Hill-Huntington method. Right? Okay. Do you have any other question? So I think that, yeah, we need to deal with some cases we're using DI minus, but in my prescribed node, it is, yeah, actually they are all the cases for DI plus, but from the, geometric mean, you can see that if it should be goes high, when your number of Q goes higher, then you can see the cases of using DI minus. So I will give you example in the next time about that. But yeah, sorry for my typos. Again, so let's deal with one more example using that one. So, okay. So a college has 5 departments, and which plans to apportion 12 new faculty positions based on the number of students in the department. And current number of students in each department is given below. So use the Hill-Huntington method to apportion 12 positions. And using your divisor, you can have a Q, which is the population dividing by the standard divisor, which is here. And you can calculate your geometric mean of Q. First one is square root of 3 times 4, which is 3.4641. And this one is also the same. And square root of 2 times 3 is square root of 6, which is almost 2.4495. And square root of 1 times 2 is 1.4142. And square root of 1 times 2 is 1.14142. So in this case, all rounded quarter is 33211. Because all the numbers has the first digit of the decimal point is 4, not 5, so they are all rounded down because it is rounding down the rounding of a Q star. So if you add all the positions, then you get 9 positions here. So here we need to use DI plus in this case. And then if you just calculate this number using your Q star, and 174 dividing by square root of 3 times 4 is 50.2294 something. And 166 divided by 3 times 4 is it is 47.92007 something. Okay, give me a second. My computers are about to die, so I'll just give him some battery. Oh, great. Then next one should be 121 divided by square root times 2 times 3. So in this case, it should be 2, 3, 49.39804 something. And in case of D, 70 divided by square root of 2. It is 49.49747. And 69 divided by square root of 2 is 48.79036. So here, the greatest number among all divisor is this 50 point something. So we will add one seat to the first department A. So adjust this seat. Okay. Is add one seat to the department A and just leave remaining for all other departments. 4, 3, 2, 1, 1 in here. And still, if you add all the number, it is 11. Oh, I calculated wrong at this point. It should be 10. But yeah, but anyway. So 11, so we need to just do one more procedure to complete it. Then in this case, all other numbers should be the same. So here, 47.9200 something, and 49.39840 something, 49.49747 something, and 48.79036 something. They are the same divisor because their seats are not changed. But for the department A, their seats is changed. So we need to calculate the divisor again using changed seat. So now it should be 174 divided by square root of 4 times 5. And square root 4 times 5 is, it is almost 38.907 something. So here, the greatest number among all is this number, right? 49.49 is greatest among all others. So we need to give a seat to the department D. So that's the final division using Hurry-Huntington method, right? And if you add all the number, then you get 12. Okay. Does it make sense? Or do you have any question? Oh, thank you, Destiny and Joanna. Yeah, there should be 10. I just fixed it. Okay, then. So yeah, so but in case of the higher number, for example, oh yeah. Yeah. So yeah, you can just, yeah. So, okay, yeah. So let's deal with the paradoxes of apportionment. So we learned about all the apportionment methods. So we learned about Jefferson method, and we learned about Hamilton method, and we learned about Webster's method, and we learned about this here Huntington method. So then, but these methods sometimes give some paradoxical distribution. What I mean paradoxical means that sometimes it is not, it seems not justifiable in some cases. So let's deal with some cases. So first one is called Alabama paradox. So the high school students was distributing this computer. So, but now instead of 46, now we have 47 computers are distributed, and we want to use Hamilton's way to distribute the computer. And for the recall of Hamilton's way, it is just calculate the quarter using your standard divisor, and we rounded it this quarter by rounding down the number, and we can just find the Hamilton apportionment for someone who got the greatest fraction part, right? So let's deal with this. For first of all, your standard divisor should be population divided by horses number of house. So here the number of computer is 47, so it is 560 over 47, which is 11.915. Right? 47. I think that's the exact number. That's not exact number, but that's kind of the, approximating number. So then your Q should be, it is 39 over this S. And if you just divide it by this number, then it is almost 3.2732. And the next one should be 71 divided by 39 over S. 71 divided by S. And this is almost 5.958. And in case of East, 18 divided by this number, this should be 1.5107. And 2 to 3 divided by S is 18.7160 something. And 209 dividing by S should be 17.5410 something, right? So in the Hamilton method, you use rounded quarter using this rounding down, right? So if you're just rounding down all the number, then those should have quarter 3, south should have quarter 5, east should have quarter 1, west should have quarter 18, and Central University should have quarter 17, right? Then if you add all the numbers, then it should be 29, 44, right? But we have 47 computers, right? So 3 computers are remaining, right? So in case of Hamiltonian apportionment, we just gave those 3 computers to the school with the higher fractional part on their exact Q, right? So if you just compare the fractional part, then South has the, the greatest fractional part, and next greatest fractional part should be the West, which is 0.710 or 16. And then next greatest part is the Central High School, which is 0.5410. So our Hamilton apportionment says that just add 1 quarters in here. So their adjusted apportionment is 3, 6, 1, 19, 17, right? Then you can just distribute this 47. right? Okay, do you have any question? So what I did is just do the same thing in Hamiltonian apportionment in the last time. Right? Okay. Then let's record the cases when we did to the using 46 computers, right? So this is what we did in the last time. And here is the last apportionment. Shouldn't 17 should be 18? Yes, you're right. Thank you, Karen. Yes, sorry, this should be 18 because we add one. Yeah, thank you. And if you just write down all those numbers in here, to here, and 3, 6, 1, 19, 18, and 47. Then the changed apportionment is for the north square, there's 0, but for the south square is 0. But for the east square, their computer was 1 down, right? So it should be -1. But west square get one more computer in here, and central square get one more computer in here, right? So all changes are happen in here. Then you can see that it is a little bit odd that even if there is a computer increasing, but the east could lose their computer, right? So it's a kind of it's called Alabama paradox. So what seems odd about this result is that east side lost a computer, even though an extra computer was distributed, right? Okay, question a bit? From what? Yeah. So in the second type, you mean? Yeah. Yes. So we are already always just compare with the first result and the second result because it is the case when the one computer is just extrally given, right? So if the case is we just give them one computer out of the distribution, then we need to change it, right? Mhm. I didn't take it one in each type. So in the third column is about the previous apportionment when we using only 46 computer. Here, the first column is just the apportionment when we use the 47 computers, right? Then last column is just how much apportionment changed. I didn't calculate anything else. So the second table is not about the apportionment, but it is just comparing them, right? Yes. So they just give the user to 46 case. Oh, okay, got it. Yeah, no problem. Yeah. Okay. So yes, so in this case, if you just comparing the same Hamiltonian apportionment of 46 computer and 47 computer, there are someone who lose the computer, right? So that's called an Alabama paradox. So first of all, to deal with what the paradox is, a paradox itself is just statement that is seemingly contradictory or opposed to common sense, yet is perhaps true, right? And this Alabama paradox occurs when a state loses a seat as a result of an increase in the house size with no change in any state population. So yeah, even if their population is not changed, but the increment of the house size, they lost the seats. So it's called Alabama paradox. And it is discovered based on 1880 census. So, and that's why they changed it to the Jefferson method. So, and so in this case, you can say that a state kind of east side. Okay. Lost a seat. In this case, it is computer. As a result of an increasing increment in the increment of the number of computer. Available, but no population changes. Right? So that's the Alabama paradox. Do you have any question? Definitely, so some small states like the east side we do not like such a situation. So that's why they want to change it to the divisor method, because it is known that this Alabama paradox is possible with Hamilton method, but is not possible with this divisor method, where the divisor method means just changing the divisor, like Webster method or Hill-Huntington method, right? And the next issue is about the population paradox. So consider two numbers A and B, and the first one, the absolute difference of two numbers A and B is just A minus B, right? So here the A always greater than B, right? But the relative difference between two numbers is A minus B over B. So sometimes you guys had a little bit confusion with this one with this equation, but this numerator should be B, which is the smaller one, smaller number among two, among A and B, right? So denominator should be the small number among A and B. So be careful about that, because in the web sign, there are some questions asking these points, right? A question? Oh, yes, times 100% to change it to the percent. Yes, thank you. So thank you, Eamon. So it should be times 100% to change it to the percent instead of just decimal number. So let's deal with some example. So compare the college's population and make cases for any change in distribution of student workers. So population in the fall 2014 was 5565, but you change it to 5573. So in that case, absolute difference is 5573 minus 5565, which is 8, right? But the relative difference is 8, which is absolute difference, divided by the smaller number, 5565. Times 100%, and it is almost the same as 0.14376%. And likewise, in case of carriage K, the absolute difference is greater number minus smaller number. Then what you can get is 10. And relative difference is the absolute difference dividing by the smaller number, in this case 3471 times 100%, then you got 0.2881%. And in case of R, just again, absolute difference is just great number minus small number. Then you got 14. And relative difference is absolute difference divided by smaller number times 100% is almost 0.36232%. And then M, it is 197 minus 198 minus 197, which is 1. So it is 1 over 197 times 100%. So it should be 0.5 or 761%. Then you can see that in the absolute difference, L has the greatest absolute difference, but in the relative difference, M has the great relative difference, right? So here is the largest absolute difference. M has the largest relative difference. So both may, both can want to increase their workers because of that result, right? So this both absolute difference and relative difference can be used to the region for argument that they need an extra worker, right? Can argue for extra workers. Then what actually I want to explain about the population paradox is that even if you have the largest, relative difference, you cannot get the worker because of that. So that's what I want to tell you in there right now. But this is the time 2:44, so I just stop at this point. So and I move on to the next time. So thank you for listening. And if you have any question, please let me know. And again, the quiz will be started on 4 p.m. today, not right now, right? I will upload it as soon as possible so that you can see it, right? Yeah, quiz is over chapter 13 and it contains 3 problems. Yeah. Last one should be 18. Karen and Dawson, which one should be 18? Could you let me know?
I'm sorry, did you ask me something?
Yeah.
Thursdays and Tuesdays lecture last week were online, right?
Yes, you are.
I was gone for a bit because of elections.
Ah, okay. Oh, I understand. So yeah, did you miss any quizzes or homework or anything else? or if you need some extension of your homework. You're looking. Okay, got it. Please let me know. Okay, thank you. Oh yes. So Karen and Dawson, you write down that there is some number 17 should be changed to 18, but could you let me know which one I had mistake? Oh, I fixed it. Oh, thank you very much, Karen. Thank you. Okay, great. Okay, if there is no other question, then I will close the Zoom session. So if you have any question, please let me know via email.